Please do.
Yes.
So, this was basically an extension of that one CMI mock question that we were doing, right? And even one earlier CMI question was of that nature, I remember.
Yes, sir.
So this is basically the theme here is um, when does injectivity imply bijectivity? Okay. Of course, here it is the function is like this from A to A. A could be infinite set, and obviously if it's finite set, there is not much to do. So along this, one question that I
Sir,
recall,
if it's um no, so if it's from A to A and injective,
hmm,
then it's automatically bijective, right? Because
no,
uh, eh,
if
no,
you
so
were
every function, like every element of A has to have an image, and it can have, because it's injective, like there's like a one-to-one mapping. So
right,
every element in the range, which is again A, is covered as well.
okay, so you're saying that f is a function from A to A injective,
Yes.
that implies it
Yes.
is surjective.
Yeah. Yes.
Okay, think about this first. Let's think about this.
Okay.
A is
Yes.
infinite. A can be an infinite
Okay.
set. Finite set, it
Hmm.
is true. That is very important and very easy, but very important. Yeah. But
Okay, infinite set. Yeah, yeah,
yeah,
yeah.
so
Then there's
then you can obviously can you quickly give a counter example?
so okay, from R to R only I'll give.
Yeah, any X could
Uh,
be anything.
so 1 over X, and at okay, not R to R, from 0 to infinity.
Hmm.
Oh, but then that's okay. No, that's a
Right.
so. What about tan inverse X? So it takes in uh it. So the domain is R. I mean, sorry, range is R. Oh, so no, 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 no.
No, tan
Domain.
inverse, the domain is R, right?
Yeah, yeah. Domain is R.
Right. And
Okay,
the
but
range
no,
is
no. Range is
minus
0 to pi.
0 to pi. Yeah, I
Oh, yeah,
suppose
yeah,
0
it's
to pi
minus.
will also work.
Yeah, but no, so the principal branch is minus pi by 2, right?
Minus pi by 2 to pi by 2.
So it's injective, but
So can
is
you
it
tell me why
surjective?
don't we take 0 to pi? Because then it will
So
not
because
be
of the pi by,
continuous. Yeah,
yeah, yeah, but
correct.
the pi by 2
Exactly,
we'll
because
have
of pi by
the
2.
discontinuity. Yes.
Right. So this one. Yeah, so this is an example, right? If you say that my range, if you take your range to be, if you take your codomain to be
Yes.
R,
Yeah, yeah, yeah.
this is right.
So it's
So
injective, but non-surjective.
not surjective, right? So we are interested in when it implies surjectivity. Okay,
Yes.
that is so. See, look, places where it implies surjectivity, it kind of means that there is some sort of finiteness going on in those places,
Okay.
right? Because in finite sets it is true, but in other infinite places also it can be true, depending on the class of function. So basically along this through this problem, then we'll get a feel for it. So f is, let's say, from R2 to R2. Okay. And what kind of function I'm going to give? It will be an analog of this kind of function from R to R. Let's say x going to, let's say x going to some constant times x. Okay, this kind of function. Okay, now you see this kind of function, where whenever it's injective, it is surjective, right? There is no
Yes, sir.
question about it.
Polynomial.
Uh, no, polynomials, I
Also,
don't
we
know.
actually did prove, not an exact proof, but like we showed that if a polynomial is injective, then it's bijective from R to R. We did that last class, sir. We
Okay,
discussed it as a
correct, correct. Then it actually follows from there. Yeah, that's nice. Yeah. That is good. But
Yes.
I'm saying that this is much simpler than that. This is just x going to c times x, right? So for any c,
Yes.
if it is injective, it means c is not zero, and in that case, it is surjective. But as you're saying, it follows from that fact also that if a polynomial is surjective, that's a very nice fact actually, right? But if a polynomial is injective, then it is surjective, right? Uh,
Yes. Yes,
is
sir.
that correct? Yes, I suppose
Yes,
so,
sir. It's correct.
right?
So we discussed it as like one elementary consequence of the Axe growth-index theorem. Like the general one is from Rn to Rn, n variable polynomial.
Right. Yeah. I'm not sure if it's from RN. I think it's from CN, but maybe it's from RN or maybe that
See,
version is
okay,
also
more
correct. Yeah.
probably.
Because R is, yeah,
Yeah.
anyways, might be true, but yeah. Anyways, that is, we will not prove that, but yeah, this one. So yeah, here I'm going to give this kind of function. Okay. I am going to give you again this. Actually, we're looking at this kind of thing last time also, so you can probably you'll be in a better place to answer this. Maybe I'll write the input like this. Okay. And the output will be A times, so A is a matrix, okay? A1, 1. Precise question is show, yeah, show the F injective implies surgery. This was one of the questions, which is elementary and at the same time it is interesting. Yeah, the Axe growth-index theorem requires complex. It's not true for reals.
Okay. Yes, sir.
Yeah.
And for this question, I'm
Yeah,
thinking.
think about this one. So this is a problem that is
Yes.
sort of very elementary. It could come up in an exam easily.
Okay. Yes.
You should think about this.
So we can fix one variable. So like we can fix x2
Okay.
as like I mean for now we take it as a constant c. Then it becomes the function becomes again like what you said. It becomes f x going to cx. So it becomes like that.
Oh, nice.
So so
Okay.
then it becomes from r1 to r1.
R1 to R1.
Yes, sir, because x2 is
Yes.
constant. So
Yeah, you're right. Because this is the first time I'm looking at it like this. Yeah,
yes.
good. And this you only want to keep. No, so how is it from R1 to R1? That is not very clear.
Oh, correct, correct. Yeah. It's still a matrix. So yeah, it's R.
So
Um.
far it is still R2. You can still maybe
Yeah.
do something, but let's see.
So,
And
so what I want to show is like if we fix that x2, then like just talking about x1, like suppose g of x1 is equal to f of x1 comma c, where c is a constant, like what we just did now. So I
hmm.
want to show that g is injective implies that g is surjective somehow.
But will G be surjective? Do you think so? No. right?
Uh,
There's a problem because G is coming from a very small place now.
yeah. Okay. Yeah.
Right? Yeah. So that approach, yeah. But what you were earlier thinking is that if you go from somehow, if you make this one dimensional,
Yeah. 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 I
then
was trying to make it one. Yeah. Yeah. Then maybe we can like talk. So what we actually get is A11 plus A12C. Okay. So now um so we have this. Um. So.
hmm,
So doesn't this give that this is subjective? Because we can make A11 x1 plus A12 to C some real number R1, A21 x1 A2 to C another real number R2. Oh, okay,
hmm.
no, 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 no. Okay, so instead of that C, we can just make it x2. Like we'll just work with what the function has given, and then it'll be a linear equation in two variables.
Yes, right. So now you're coming to the linear equations. Yeah, that may be a more fruitful approach, right, in this
Yes,
case.
yes, sir. So like we can drop the C and just work with the x2. And first row can be made any real number, so can the second row.
Okay, but what is the but why you're not using the injectivity? So certainly you need
Yeah.
something is missing.
The so the
Think about it.
so
Think.
somehow we have to show that injectivity implies that the linear equations are consistent,
Yes, right.
because otherwise, because that's the only place where we get a problem while solving linear
Yes.
equations.
Yeah. Now I'm using constants,
Yes.
but maybe better to use y. So what? So first you should just think like, what does this being consistent mean? And
Uh, s- yeah. Uh, like A11 by A21 is not equal to A12 by A22.
right. And we will translate this into our language. This is not a constant multiple of
Yeah.
the other one,
Yes, sir.
right? Or maybe no, no. You same, right. Now you should just prove that this is true from the injectivity.
From injectivity, yes, sir. I'm actually having a like hard time visualizing injectivity for like this function.
Huh. So we had discussed this. So maybe last time we said about injectivity something. What injectivity means. So injectivity means that to different points go to different points, right?
Yes, yes, sir.
And yeah, now can you tell me that what is, so this is the image of something
Hmm,
under this function f. It is the image of what? So it is the image of 1 comma 0.
correct.
This is this, yeah.
Yes,
This should be taken
yes,
as a
yes.
standard thing, not just a trick, right?
Okay,
And then
yes,
you
yes, sir.
this is the second column. Second column is the image of that.
Yeah.
And you
So
want to
like the
say that,
basis.
right. So these two you want to say are so these two lines are not collinear,
Hmm.
right?
Correct.
So
Yes.
now you can try to visualize that if the input is this and this is the input, and they are obviously not collinear, then this is the input space. In the output space, if they become collinear, then what goes wrong?
Then
Then it
okay.
cannot be injective. It's
Yeah, it
impossible to
cannot
be,
be injective. Yeah,
right?
because like they're coinciding.
Right. Because then everything, then any vector will land on this line only,
Correct. Yes,
right?
sir.
But we will still write it down because this we said last time also, but I think it was not concrete enough, right? Yeah. Meaning
Yes,
that
kind of.
if you sit and write, it will come, but we should just write it down now. Yeah. So, uh, okay. So all we are saying is that f of 1, 0, okay, if this is equal to f of 0, 1, or some constant or some multiples, right? Some lambda times, right? This is what
Yes,
we are. If this happens, if this happens, this
it
basically
cannot
is the
be
same
injective.
as this, right? If this
Yes,
happens, then you see, then you can use the linearity, and you will get um, 1 minus lambda going to 0,
right.
right? Because this is how you want to say, or actually, even better, as you are probably thinking, even better, just put the lambda inside, more with standard what we know in high school, two different points going to same point, right?
Right. Yes, sir.
Yeah. So you just say, if you want to write it very cleanly, if this equals to this, right? Then basically you get this.
Yeah, and it'll be non-injective then.
Then that is basically non-injective. Okay. So now you've got a geometric field, but you have to translate that, right? That we're not
Yes.
doing it very, very properly, but you should just feel it enough so that you can do it when it's needed. Okay. So, right. So see, this was a very easy thing. And here you can
Yes,
see
sir.
that there is, even though the domain is infinite, range is infinite, R2 and R2, there is something about these functions which is finite. By all means, these functions have a finiteness field, right?
Right.
Why?
It's like you said, so it's the analog of x going to cx.
Yes, constant multiple. It's an analog of that. And also in another ways, like it's sort of like the range is determined by the output of these two vectors, right?
Right.
So the
Right.
range
Yes, sir.
range is determined by just finitely many things, right? So it's basically what happens between two finite sets determines the entire nature or entire function, right? So yeah, so those things are there. Yeah, I mean, one
Yes.
can say this more directly from what we did last time, but let's not go into that. Otherwise, we will get a little, yeah, a little off the page. So yeah, now you can. It's up to you. You can think about more of this. Yeah. So
Yes.
right. Yeah, a good place to read more about it. Reading books, can be very important here. You can just like the art in that we are solving chapter one problems. You can read a bit of theory from there. Just sit and
Okay.
read for
Yes,
some
sir.
time. Yeah, you will see
Now
that.
I need to brush up on my matrices because
Yes,
I
and
only know high school matrices. Like
yeah,
I don't know
yeah,
much more than
but
that.
but you have idea of these things. You can work with, like, you can combine different techniques. But if you read that, then that knowledge will be very, very useful. It's few pages. You can
Yes, sir.
use it in many, many places. Okay. So this is just one instance, right, where injectivity implies bijectivity. Of course, we saw uh, for polynomials also it is true, even from R to R. That was nice. And for finite sets, this is true. Okay. Um, yeah. So right. Yeah. So of course, this will be true in many places, I think, but they will probably be beyond our scope. So now we will go into this. This is another kind of thing which we were discussing, injectivity and left inverse. So
Right. Yes, we did this
yeah,
last class.
last class also. And but there was one lemma which sort of we have to still, there was a part of the homework, injectivity and left inverse. So so the CMI question was this, right? That if f is a function, f is from whatever from a to b, okay? So if there exists a g such that f of g of x equals to x for all x, then this implies f is injective, right? So this is something which we all know, but we want to prove the converse. No, yeah, we want to prove the converse, right? This is okay. This implies f is injective, that we did, but we want to look at this. So f from a to b is injective. Okay. Show there exists. Yeah, you're right. We did this last class for matrices. We actually explicitly, found the left inverse. For bijective, continuous
Yeah.
bijective functions from R, we showed that I gave that as a homework that the
Yes.
inverse is continuous. So those are fine. But now we just for sets, we want to see if we can prove it. Prove this. Show there exists a G, and this also you should just think about B to A. And this G is not injective. I mean, I'm not saying this G is injective, but just some G from B to A such that f of G of x equals to x for all x in A. So think about this.
So do I have to like construct a function or just prove existence?
I mean, proving existence is enough, of course,
Okay.
but
Okay. Yes.
yeah, but you may have to construct I mean, yeah.
So from the range of f, we can just say suppose y belongs to the range of f, which is a subset of B. We can say that g of y
Hmm.
is equal to x. So where y is equal to f of x. So just explicitly like saying it like that. And since f is injective, what happens is we don't get any inconsistencies. Like g is not being given the same value and asked to send it to two different values. because f is injective.
Right. But okay, so this y is equal to some f of x, and then
Yes,
you send it back to x, not f of x.
yes, not x, not f of x. Yes, x. So we pick up some y, which is
Yes,
in the range of. So it's it's an image under f. So then we just say g of y is equal to x. And
right.
again, we need injectivity here because if it were not injective, then what would happen is we would be getting two distinct values of x, but then the image of the input for g would be the same. So
Yes,
we would be, it would not be
right. So
well defined.
injectivity is certainly a necessary condition, right?
Yes, yes,
So yeah, so basically, such a function exists implies injectivity. That we have even proved explicitly that this condition means that it is injective. But the problem you see now is that you have not defined G on all of B.
Hmm. Uh, uh, it can be anything, right? So because oh, well, since we don't require G to be injective or anything, for the elements of B that are not in range F, if
Hmm.
any, we can send them to any arbitrary element of A.
Right, correct. No, that is
Yes,
correct. Yeah, only that when you say something like this, then that is just there is a axiomatic problem, because basically this is an
uh,
infinite set. Okay, and
yes,
for this infinite set, you're saying you pick a point and you send it uh, anywhere, right?
yeah.
Uh, so the problem is that is not a well-defined thing because it's an infinite set. Okay.
Okay, then we can just send it to, we can send all of them to like only one instead of sending them to different. We just send
Hmm.
everything G. If X is in B minus range of F, we send
Hmm.
it to a fixed X1 in A, some X1.
Yes. Is that yeah, that sounds consistent. That sounds consistent to me.
Right. So like I don't know the axioms which we're working with, and even if you like tell me that we're working with these
No.
axioms, I don't.
Yeah, I think that is good enough. But let me just look at it.
Yes, yes, sir.
Whether it I think you're correct. I don't, as you say, right? But if you send it to a fixed element, then really that seems okay, right? Yeah. That is, you don't need anything. Yeah, correct. So the only thing that I was slightly worried about is the following. Like if you look at, but that's not a problem because you send it to a fixed thing, and that is because there is one fixed thing that you can send everything to, right? So, but only one thing that is there is if you look at this, and yeah, now you are sending this to anything, right? But otherwise means in general what you need to do means what the situation. So this is part of this general situation that basically there is this xi, right? So xi in this, right? And for xi there is a set capital Xi, and you need to send xi to something in capital Xi, right? In this case, that capital Xi is all equal to A in our case, right? Because this Xi, you are sending it to something in A only, right? And that is why you are able to say that you just fix one thing and you send everything to that one thing, right? But this could be part of the general structure where each Xi has to go to some set, or for each Xi you have to pick something from the set capital Xi, and this capital Xi may be different for different small Xi's, right? Then you see that thing, if there are infinitely many small Xi's, then that thing becomes a problematic thing. Then that you see, you cannot, like when you try to say it, you see that you're not sure if it really forms a set. For example, if it's like x1, x2, dot 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 dot, and for each of them you have the set. In our case, they are all same. But now for each xi, you have to pick something from capital Xi, right? And you form an infinite tuple. That actually, so the thing is that actually does not follow from the axioms of set theory that you already know. So for that, you need what is called
So
axiom of choice.
axiom of choice. Yeah, I was
Axiom
going
of
to say that.
choice, right?
Yeah,
Yes. So, uh,
and like from what I know, there's some controversy. Not everyone accepts it, and uh,
right. Yes. So basically,
whatnot.
yes, yeah, it is something that should be true, but it cannot be proved to be true from the other axioms. Okay, so it has,
Actually, like I was watching a video,
huh?
and someone said that what follows from the axiom of choice directly is induction, but on R. So something like that. So that it
Yes,
implies that R is well ordered somehow.
right, exactly. Yeah, yeah, exactly. That is, there are three versions of it. One of it is well ordering principle, and that says that any set can be well ordered, but the order may have to change. Okay, and then there is another one called axiom of choice. Axiom of choice is already there, and there is On's lemma, which is
Okay.
which is basically, that is basically like induction. Okay. Um, yeah, it's basically like induction, and if it is it's saying that basically if you have a family of objects, and if you look at any sub collection in that family where which is sort of increasing, okay, and now if it has a upper bound, if every sub collection which is increasing has an upper bound, then there is an element in that family which is sort of maximal. Okay.
Okay. So it's
Yeah.
like the opposite of what well ordered. Like well ordering is minimal element, and this is maximum.
Well ordering is minimal element.
Yeah, at least
Yeah,
for
correct.
natural numbers, like what I know,
Yes, yes,
it's
yeah,
minimal.
correct. Yeah, that is correct. Well ordering is about every subset have a minimal element, and Boson's lemma is more like yes, correct. No, yeah, yeah. Boson's lemma is, yeah, it is. 1 minute. Yeah, it's an existence thing that there is a maximal element. Yeah, yeah. It's also something that should be true. Well ordering principle is something very strange, but John's lemma and axiom of choice are not strange, and that is the problem. That, yeah, something not strange, but if you assume it, then it gives you things which are strange, and that's why maybe there is a controversy that some people don't. Yeah. Anyways, so this is the situation, and